Okay, well, good evening, everyone. So I'm going to talk this evening about computer vision, which is the science of understanding images. So I'm going to start the story at the beginning. The invention of photography, 1827. The world's first permanent photograph was captured. And in that year, the world had maybe a handful of photographs were captured in the entire planet. Last year, the world produced over 1 billion digital cameras. 3/4 of those were in your phones. And we love to use our cameras. So the Facebook users upload over 900 million photographs a month. If you look at the amount of data on the internet, the text of every web page on the whole internet is a tiny dot compared to the amount of information in the digital photographs. And this is what a photograph looks like. It's just a matrix of ones and zeros, a matrix of numbers. Each of those numbers records the intensity of the light that fell on the sensor of the digital camera at the moment when the shutter closed. So the science of computer vision is about trying to understand, is this a photograph of a cat or a photograph of a car? How can we know? The only thing that we can do, the only thing a computer can do, is to add and subtract and compare those numbers. So what on earth is that image? The task of computer vision is to try and find out. Now, it might seem strange to you, but everyone in this room is an expert at this task. If I show you that image a little differently, instead of showing you those numbers, if I show it to you as the intensity of the light, immediately it's obvious to you what you're seeing. And that's because your brain is doing an amazing amount of processing on that image. So when the image falls, when the image travels through your eye and falls on your retina, what's transmitted up your optic nerve, across the optic chasm, along the optic tract to the back of your skull, it enters the visual cortex. And in the visual cortex, your brain is going to do a lot of additions and subtractions and comparisons on those numbers. So what reaches the visual cortex is just a digital photograph, more or less. It's a series of intensity recordings transmitted from your eyes. And so at the time this reaches your visual, by the time it traverses your visual cortex, no longer is it just a series of numbers, but it becomes something that's understood. Concepts and geometry and rich understanding. So what we'd like to do is reproduce that in a machine. Now, although you perceive the visual world without effort, it's actually, or without conscious effort, it occupies about 30% of your brain, just processing the input from your eyes. So why do we want to do this in machines? It's an immensely difficult task, but if we could perfect the science of image understanding, suddenly the class of things that we can do with a computer becomes vastly larger than what we can do today. Instead of having passive machines that sit on your desk and display your email, all of a sudden we can have a machine that deals with the content of the real world. We can build autonomous machines because they can deal with sensory input in the way that you can deal with sensory input. Instead of sitting on your desk, they can start to move out and explore the world. And so that enables a whole lot of things, basically the science of robotics. It enables extraordinary science. So this is Spirit and Opportunity, the NASA rovers, which are doing geology on the surface of another planet where no human has ever been. And they're doing it partly because they have computer vision capabilities that allow them to operate without having a human directly control their movements. It also allows us to do dangerous things. So this person is disarming a sea mine. He should not be doing this. No human should ever do this task. So we're going to build machines that allow us to do these things for us. We're going to automate our transportation system. This is Junior. It was a robotic car developed by Stanford University. It's traveled hundreds of miles through city streets and across the desert without anyone behind the wheel. One day when you're drunk, it's going to drive you home from the pub, and it's going to put an end to the daily carnage on our roads. And of course, for economic reasons. So if we can build autonomous machines, it's going to transform our economy in a way comparable to a sort of a second industrial revolution. On the left here, we've got an automated container terminal in Australia. It's shipping 24 hours a day, 365 days a year, using automated perception algorithms to figure out where the containers are and move them around. On the right-hand side, this is an automated warehouse using robots from Kiva Systems. It's already fulfilling your internet orders, making the things that you buy cheaper. Hooray. So now I want to tell you a little bit about how this is done. Because not only is this a very important problem, but in solving it, we're forced to confront some of the deepest problems in science. Because to teach machines to see, it turns out that we have to teach a machine to learn. So I want to come back to sort of one of the holy grail problems of computer vision, which is category recognition. So we're presented with an image, and the question is, what's in the image? So let's just take a really simple binary task. Does the image contain a bicycle? Well, if we remember, this image to the computer is a matrix of numbers. So somehow we have to add and subtract and compare these numbers and decide if there's a bicycle in the image. So you can think about it like writing formulas in Excel. And that's exactly what the machine is doing, adding and subtracting and comparing these numbers. So how on earth are we going to design something that's going to say whether or not there's a bicycle in the image? And because, you know, bicycles come in all sorts of different shapes and sizes. We can see them from different angles, different colors. But we know it's possible because your brain is doing it right now. Your brain is adding and subtracting those intensities of light and determining that there's a bicycle in all these images. So how can it be done? Well, perhaps we can lock someone in a room for years, and they can figure out ways to add up and subtract these numbers. And maybe years and years later, they might come up with some sort of formula that detects bicycles. Who knows? Maybe it's possible. But maybe tomorrow, instead of detecting bicycles, we want to detect cars or penguins or who knows what. We might have to start from scratch. So the approach that's been developed in the community is not so much a sort of a hand-coded approach. We want to teach the machine to learn from examples, so that if tomorrow we come up with a system today that can learn how to detect one category, well then tomorrow we can just give it a different set of training examples and it can learn to detect that one itself. So the way it works is that if we want to detect a bicycle, what we do is we give the system a lot of examples of bicycles and a lot of examples of non-bicycles, and it's more or less going to dream up a lot of random rules that try and split one category from the other. And there's a lot of interesting mathematics in this. To say it's random rules is a bit simplistic, but essentially the system learns the rules itself, and we reward the rules that do better and penalize the ones that do badly. I mean, there's quite a lot of sophistication here, which I can't really go into, but essentially the machine is going to come up with the rules itself. And this has been quite a successful approach. So this is a state-of-the-art recognition result, and you can see that the machine has quite well segmented and categorized the objects in the image. But machines being machines, they get a lot of things wrong. And we're definitely not there yet. This is a kind of a holy grail problem. So this is the kind of result that you sometimes get. So you and I know the tennis player isn't backhanding a lemon, right? But the reason that we know that is that we have this vast amount of experience in the world. We know an awful lot about the relationships between concepts. So we're asking a lot of the machine. How on earth are we going to get to that point? Well, we're getting there. It involves digesting more knowledge and more training examples, but there's a long way to go. Here's another example of it getting wrong. I like to show these. So this is, the machine's task was to find pictures of zebras. So it came back with these two, and it also came back with this. It's like, well, let's learn something. It kind of knows what a zebra looks like, but it's not quite right. And sometimes it's just plain wrong. So this is, please show me, it says highlight the pedestrians in the image. And, it's found one, but it also thinks the top of the lamppost is a pedestrian. No human is ever going to make that mistake. And we can do better than some of these examples, but this problem of category recognition is the holy grail of my field, and it's a lot of work still to be done to get there. But I wouldn't really be up on stage tonight unless I had some really cool things to show you. And there are some things that we can really do at this point to a very high degree of success. And a lot of those have to do with understanding the geometry of images. So one of the first examples I'm going to show you is by some work at Carnegie Mellon by Derek Hoym and Alyosha Efros. And what they did was that they said, let's take a photograph and work out the basic geometry of that image. Because inside every photograph, there's a kind of a little world. You can work out, you can look at a photograph and you can imagine, if I was standing somewhere other than the cameraman, what would the world look like? And so what they did is they got the computer to do that. So now you can take a photograph and you can kind of fly into it and explore the little world inside it. So I'll have a look. So here's the photo. Then the computer works out what the geometry is like. And you can see the world from a different point of view. It's really doing a pretty good job of imagining what the world might look like from somewhere else. Right. Okay, so this is the second example. And this example is something called augmented reality. This was developed by George Klein and David Murray at Oxford. And so what's happening here is that the camera is tracking little features in the image, which you saw there at the start. And by tracking those features, it knows where it is very precisely. And because you know where the camera is, you can draw virtual objects into the scene. And you can draw them in such a way that they're consistent with everything around them. And so it's as if there's something new in front of you. And you're going to see a lot of this in the next few years. It's going to be everywhere in about 5 years' time. And mostly, I was talking about sort of revitalizing the economy and solving the world's problems and driving you home from the pub, but I think a lot of what you're going to see with this is going to be games. So this is an example where my friend was visiting a Zen rock garden. He got a little bit bored, so he decided to add some of his own features to the rock garden, and he started playing Darth Vader's Ewok Rampage, which is an augmented reality game of his own creation. So the joys of augmented reality, the wonders of science. Right, so now I'm going to talk a little bit about what I do myself. So my day job is making visual search engines. So we're all familiar with search engines like Google, where you go to the internet, you type something into the box, and it finds something relevant to what you typed in. So that's a text search engine. Now there's another type of search engine that's been developed in the computer vision community, where you take a photograph of something, we analyze what's in the photograph, and find something relevant to that. And this is what we develop. So if we can have the cameraman on stage, perhaps we're going to do a live demo of how this works. So what I'm going to do, I have some photographs here, or some paintings. And I have an app on my mobile phone, which is something that we developed at Plink. Okay, so the way this works, as I said, it's a search engine, but it's going to work by taking a photograph. So here's our app when we start it up. And so what we're interested in doing now is I've got some postcards here, and you wonder, I wonder who painted this picture. So we just take a photograph. And it doesn't have to be a very good photograph, if you can see that on the screen there. And so I just send that photograph away to the server. It matches it against its database of images. And there you can read all about it. So you can see there that this was Bathers at Agnières painted by George Seurat. And just to demo, this is really, it works with really quite bad photographs. So I'm going to sort of take my heart in my mouth here and give it a really bad photograph and see what happens. So if I try that, that's not a great photo of a horse, right? If I send this away, it doesn't work. We'll try again. Maybe I was trying too hard, right? Let's try that. Okay, so there we go. It tells us. So that's how visual search engines work. You take a photograph, it gets analyzed by the server, we send you back information. We can search millions of images in a fraction of a second. And it works, as I said, with bad photographs. So we can match these images here, really funny angles, and like I said, this is a real example that worked. So we can take very small amounts of the image, sort through these images very quickly, and find the matching examples. Now the funny thing is that even though the system can tell you that this is Whistle Jacket painted by George Stubbs in 1762, it has absolutely no idea that it's a horse. So, like everything in computer vision and AI, it's a kind of idiot savant. It's brilliant at some tasks and absolutely useless at everything else. And only by combining a lot of these systems will we be able to produce anything that has capabilities a little bit like the human visual system. We have a long, long, long way to go. But we're building some of the parts, we can do some cool things, and we're on our way. So I'd love to tell you a bit about how these systems work, but I couldn't fit it into 18 minutes. So you'll just have to take my word on it. I think in 5 minutes' time you might understand. But I think I'm going to leave it there. I hope you've learned something. I hope you enjoyed it. Thank you very much.